For years, recurrent neural networks processed text strictly step by step, but they suffered from a recurring memory leak. As the network passed its notes along, the influence of early words faded out, meaning the model lost the start of a paragraph by the time it reached the end. In 2017, the transformer architecture solved this by abandoning sequential reading. It allowed every word in a sequence to look at every other word simultaneously. This parallel processing meant workloads could be spread across thousands of GPU cores at once. For the first time, researchers could train models on web-scale datasets, leading directly to the fluent chatbots we use today. But the very mechanism that enabled this massive ingestion of data is the same one that creates its most severe limitation. This grid illustrates a math problem known as the quadratic wall. Because every token must compare itself to every other token, the workload scales quadratically. Double the length of a document, and the number of comparisons quadruples. A 100,000-word context requires 10 billion individual operations. Holding on to that web of comparisons requires a massive cache of data. As sequences grow, the system will eventually exhaust the physical memory bandwidth that is available on even the most powerful hardware. When the system is fed too much text, it struggles to compress the context. Empirical tests show that when a model is overwhelmed by thousands of tokens, it often loses track of salient facts buried in the middle of a document. Buying more computers doesn't solve this. Mathematical proofs based on the strong exponential time hypothesis show that we cannot maintain this level of precision while increasing speed. The universe imposes a no-free lunch rule on this specific architecture. The hardware limits expose a deeper issue in how these models think. A transformer is optimized to maximize the likelihood of the next token. It is a statistical engine completing local semantic correlations, not a logic engine engaging in rule-based reasoning. This creates the reversal curse. An AI can be trained on the fact that A's father is B, yet it will consistently fail to deduce the inverse, that B's child is A. It has learned a word pattern, but not the underlying relationship. This is the binding problem. The model's representation of an entity is often fragmented based on its grammatical role. Jennifer Lawrence as the subject of a sentence is stored in a different vector space than Jennifer Lawrence as the target of a query. Because these systems only guess what sounds most plausible, hallucinations aren't just errors, they are an intrinsic property of the math. When a model favors syntax over semantics, it hits a glass ceiling where true understanding remains a simulation. To break the quadratic wall, researchers are designing alternative architectures. One is Mamba, which uses a selective state space. It acts as a smart memory knob, dynamically choosing which incoming tokens to remember and which irrelevant noise to discard. Another approach is RWKV. It restructures the power of attention into a tidy, recurrent framework. It runs step by step to save memory, allowing it to process million-token sequences with the fixed memory efficiency of an old-school RNN. Liquid neural networks draw inspiration from the biology of the C. elegans nematode. These networks feature a fluid time constant, allowing them to adapt their processing speed and memory duration based on environmental surprises, all with extreme parameter efficiency. Finally, test-time training layers treat the model's hidden state as its own learning task. As the model reads, it quietly updates its own weights, constantly compressing the historical context into its synaptic memory at test time. These models suggest we can achieve massive processing throughput without the catastrophic memory costs of the original transformer design. But efficiency doesn't solve the logic gap. Yann LeCun's JEPA architecture suggests we should abandon word prediction entirely. Instead of guessing the next pixel or token, JEPA predicts abstract embeddings, learning the physics and structural relationships of the world through observation. This leads to a mouth versus brain framework. A separate energy-based world model acts as the brain, validating the causal truth of an idea. It then passes that validated belief to a frozen language model, the mouth, to be rendered into text. We are also seeing the rise of neurosymbolic AI, which pairs neural perception with a strict logic engine. It mimics Daniel Kahneman's theory of human thought. A fast, intuitive System 1 handles the messy data, while a deterministic System 2 checks the work against hard mathematical rules. By moving the burden of truth away from the language generator, we can build systems where logical validity is a hard-coded constraint rather than a statistical guess. The transformer isn't becoming obsolete, but its era as a solitary, monolithic architecture is ending. The current research points toward a deep hybridization. This means stitching together the fluid perception of neural attention with the memory efficiency of state space models. Adding test-time training, logic layer acts as an immutable truth checker. The industry is shifting away from the brute force scaling of parameters and toward targeted structural innovation, designing models for causal deduction rather than just vibes. The last decade successfully taught machines to mimic the patterns of human speech. The next phase of development focuses on grounding that fluency in the logical rules of reality.
Praxiotech Research.